So it's going to be 3.3.
So can you read the problem to me?
Sure. For a equal 1 through 5, find the smallest integer k, and I'm assuming that should be the smallest positive integer k, because otherwise we could put 0 in there and have them all equal. The smallest integer k such that a to the k is congruent to 1 mod 6.
Okay, so
a is 1 to 5. Find the smallest integer k such that a,
right.
yes, a to the
So we want
k,
to solve the congruence, a to the k congruent to 1
mod 6,
mod 6
where
for
a is 1 to 5.
a equal 1, 2, 3, 4, and 5. And we want to find the smallest positive integer k.
Right, I'm assuming that's what it didn't say smallest positive, but
No,
I'm assuming you.
But you're right.
Yeah.
No, it should have said smallest positive. So, well, for a equal to 1,
right.
1 to the k is congruent to 1 mod 6. So k is equal to 1.
Yes.
For a equal 2, 2 to the k is never congruent to 1 mod 6.
That was my question.
So k does not exist.
Okay, keep going. I have some
3
questions
to
after
the
you're
k,
done.
4 to the k. For none of these,
Bless you.
you can solve the congruence. And for a equal 5, the smallest positive integer is 2. 5 squared is congruent to 1 mod 6, so k is equal to 2.
Okay, that's what I came up with. Can you explain why a k that mathematically what's going on with k not existing?
Okay,
Because
so if the greatest common divisor of a and 6 is bigger than 1, then you can solve, then a to the k is congruent to 1 mod 6. What does that mean? That means if and only if k minus 1 is some multiple of 6, or 1 is a to the k minus 6q. But suppose this greatest common divisor of a and 6 is some number d, which is at least 2. Then this is divisible by d, because d divides a and d divides 6, but d does not divide 1. So, well, maybe I should just put it like this. Suppose we let the greatest common divisor of a and 6 be the number d. Then a to the k is congruent to 1 mod 6 if and only if a to the k minus 1 is a multiple of 6, or 1 is a to the k minus 6k, which happens if and only if d divides 1. So the only way this can happen, the only number that divides 1, positive number that divides 1, is 1. So the only way a to the k can possibly be congruent to 1 mod 6 for some k is if a and 6 are relatively prime. 2, 3, and 4 are not relatively prime to 6, so there's no possible solution of this congruence.
Thank you.
That's supposed to be 6q. What is a to the k minus 1 equals 6? What is that?
6q. That just means
some multiple of 6, right?
Multiple of 6.
Yeah, I get it.
I have a question. I noticed you skipped over solving systems of congruences. Are we going to be responsible for being able to solve systems?
That's the Chinese remainder theorem, and I skipped that.
Okay, thank you.
Other questions?
Professor, you sent out a chapter on the group theory. So
Yes,
that is in place of the book or in addition to the book?
it's in place of the book. There's too much in the book. So I'm taking, and that's actually just the first part of a section on group theory. It's called Topics in Group Theory, I think. So that is instead of the book, because in the book, there are probably 200 pages, and that's too much. So
Okay.
just so you know what it is I'm covering, I'm putting that into a separate set of notes.
Okay. As an unrelated question, I assume that you typed up all these books using Microsoft Word?
No, no one uses Microsoft Word for science or any kind of scientific writing.
That's what I was wondering. What do you use, Professor, to type these things?
Everyone in the world uses a program called LaTeX, L-A-T-E-X, which you download for free from the internet. It is
Okay.
a standard mathematical and scientific typesetting program. Every
Okay,
time you
thank
see
you.
a book,
I was wondering that
it's all
because
done in LaTeX.
LATEX, latex?
L-A, it's usually written like this,
Got you.
but
Thank you. Because I was wondering that it was very nicely written and it would have taken a humongous amount of time in Word. So I was wondering that. Thank
in
you.
fact, in science, certainly in math and physics, anytime you write a paper or a book, it is required that it's written in LaTeX. Publishers won't accept it otherwise.
Understood.
I have one more additional homework question, Professor.
Go ahead, happy to do it.
Homework 3.1, number 11.
Okay, can you read it, please?
Yes. Let m be an odd integer. Prove that the set 0, 2, 4, up to 2 times n minus 1 is a complete system of residues modulo m.
Okay, so let m be an odd integer. So for any integers k and l, we have 2k is congruent to 2l mod m if and only if m divides 2k minus 2l. That's what a congruence means, which means m divides 2 times k minus l. So 2k is congruent to 2l mod m, means m divides 2 times k minus l. But m is an odd integer, which means m and 2 are relatively prime. And by Euclid's lemma, if m divides 2 times k minus l, and 2 and m are relatively prime, then m divides k minus l. So we have 2k is congruent to 2l mod m if and only if k is congruent to l mod m. So what does that mean? So the numbers 0, 1, 2, 3 up to m minus 1 are pairwise incongruent, not congruent, mod m. Because the difference between any two of these is strictly smaller than m. And since these are pairwise incongruent mod m, it follows that if you multiply by 2, 0, 2, 4, 6, up to 2m minus 2 are pairwise incongruent mod m, and there only are m different congruence classes mod m, so this set of even integers is a complete set of residues modulo M. That's the proof.
Okay, just one question. In question 11, it gave us a set 0, 2, 4, up to 2 times m minus 1, which, okay, you distributed it. Never mind. Silly question. Thank you.
Okay.
Professor, question on the reduced system modulo M. So the Euler 5 function for any integer, any number, which is basically gives you the cardinality of the reduced modulo set, is that always going to be even? Because that's what I think it is. It's always going to be an even number. Is that correct?
Well, so suppose you take the modulus M equal to 2. How many
Except for
congruence
2.
classes
Except
are
for so I should have qualified that for numbers greater than, let's say, 3 or let's say even 5.
So the answer is yes. It's always even from some point on.
Okay.
In fact, it's always even
From 3
except for
onwards,
M
I think.
equal to 2.
Right. Okay. I suspected that, so I just wanted to confirm that.
I'm assuming no one has any other specific homework questions. Could you also review the properties of groups and rings and how they differ?
You mean how a
Briefly.
group is different from a ring?
Well, yes, and I guess from time that I have a question to ask you.
Well, so a group,
Something is defined as a group subject to a binary operation. So it's a group
well, no, it's
from
not. You shouldn't
addition.
say the word subject to. If you have
Okay.
a set with a binary operation,
Yes.
that set may or may not be a group, depending on whether the binary operation, let's say some way of multiplying 2 elements in the set, satisfies the properties of having an identity, having every element having an inverse, and the associative law. So a group is a set with a binary operation that satisfies those 3 properties.
So for instance, the set of all integers is a group for addition, but it's not a group for multiplication.
Correct.
Okay.
It
And
has
then,
a multiplicative identity, which is 1. It satisfies the associative law for multiplication, but it is not the case that every element has an inverse.
right. So just sticking with the integers then. So over the integers, they are a group with respect to addition, but not multiplication. And then beyond that, since they're a group over addition, when you add in commutativity, it then becomes a commutative or an abelian group as well on addition.
Correct.
Okay. So now the extension to rings is then
Well, so don't
what?
think of an extension to rings. A group has 1 operation, addition or multiplication. A
Okay.
ring has 2 operations, addition and multiplication. And under
Okay.
addition, it must be an additive abelian group. And under multiplication, it is not a multiplicative group, but it does have to satisfy certain properties.
So
Multiplication has to be associative, there has to be a multiplicative identity, and you have to satisfy the distributive laws, addition over multiplication.
So since the integers are not a multiplicative group, the integers are also not a multiplicative ring. I mean, they're not a ring because they're not multiplicative.
No, it's not true. The integers are a ring. If you take the integers with the usual addition and multiplication, with respect to addition, you have an additive abelian group. If you
Yes.
look at multiplication, multiplication is associative. There is the identity element 1, and you have the distributive law. A times B plus C is AB plus AC. So the integers with the usual addition and multiplication do form a ring.
Okay, see, that's where I've kind of gone off the ropes here.
So a ring is an additive abelian group, which also has a way to multiply elements, and the multiplication satisfies the associative law. It has an identity and the distributive law.
Okay.
So for example, the rational numbers also form a ring. The real numbers and the complex numbers form a ring. If you take the congruence classes mod M, that also is a ring. It's a finite ring, has M elements.
Okay, I'm going to have to go over that again, but it's becoming a little more clear. Thank you.
Professor, in your new homeworks for this week, section 1.1, I guess that refers to the chapter that you sent.
Yes.
It says questions 1 to 4. I had a couple of questions regarding that. So
Okay.
do you, so in terms of question 3, which basically defines a 2 cross 2 matrix, where basically the M of MA is simply 1A, which is a first line, and 0, 1. And the part B of that question says that show that that set of that matrix is isomorphic with Z by constructing a one-to-one and onto function. So I was wondering, isn't that simply like, you take any element in Z and just plug it into that matrix, like let's say a number M or a P, then M of P would be just 1P and 0, 1, and that would be one-to-one and onto as well.
Right.
So,
okay, so that is correct. But let me for everyone's benefit, talk about this notion of isomorphism of groups. So we can have two groups that have different elements, but in some sense they're the same group. They just have different external appearances. So let G and H be groups, and isomorphism, this is a definition, is a function f from G to H that has two properties. First, f is one-to-one and onto. I'll remind you in a minute what that means. And second, for all elements x1 and x2 in G, f of x1 times x2, I'm going to write the operation in the groups as multiplication, but you can translate it to addition if that's the operation. F of a product of two elements is the product of their images. So you can think of it like this. Here's the group G. Here's the group H. And we have some function from G to H. So if you take an element X, it goes to some element f of X. If you have, now, so what does it mean to be one-to-one? So f is one-to-one means that it cannot be the case that there are two different elements in G that get sent to the same element over in H. That can't happen. So it means that if you have f of x1 equal to f of x2, that can only happen if x1 equals x2. So if you take two different elements, x1 and x2 in G, they have to be mapped to different elements over in H. And so that's what one-to-one means. And what onto means is if I take f onto means that for every element y in H, there's something in X in G. There exists X in G such that f of X is equal to y. There's some element in X, some element X in G that gets sent to Y. So you can hit everything in H from something in X under this function f, and any two elements in G get mapped to two different elements in H. And there's a fact in set theory, or it's actually calculus, you see in calculus, that if f from G to H is 1-to-1 and onto, then you have a function, I'll call it f to the minus 1, from H to G, which is the inverse function, such that if you take an X, f sends it to H, f inverse sends it back to G, f inverse f times f of H is equal to X. And similarly, for any y in H, if I take y, f inverse maps it to G, f maps this back to H, and it always gets back where you started. So whenever you have a 1-to-1 and onto function between sets, there's always an inverse function that goes in the opposite direction. And we say that two groups are isomorphic if there's a 1-to-1 and onto function between G and H, which has this property that if I take x1 and I map it here, and x2 and I map it here, and I multiply these two things, so I get f of x1 times f of x2.
You missed it.
Back here, I could have multiplied x1 times x2, and x1 times x2, what that gets mapped to is f of x1, x2 is equal to this. So if I take two elements here, multiply them and transfer them to H, I get exactly the same element as if I just took x1 and mapped it to H, x2 and mapped it to H, and then multiplied over here. So that's what this sort of functional equation says. And two groups are said to be isomorphic if there's a function between them that's 1-to-1 and onto and satisfies this very pretty property. So there's a homework problem where I say, look at the set H of 2-by-2 matrices. So let me put it like this. First of all, for every integer A, define the 2-by-2 matrix M sub A, which is 1A, 0, 1. So this is a matrix. Well, it's a 2-by-2 matrix. That's what it is. And let H be the set of all of these matrices for every integer A. Now, I claim this set is closed under matrix multiplication. So you have to know how to multiply 2-by-2 matrices. If you take MA and MB, that's the matrix 1A, 0, 1. MB is the matrix 1B, 0, 1. If I multiply them, I get 1, A plus B, 0, 1. But this is a matrix of this form. That's the matrix corresponding to the integer A plus B. So among other things, this says that H is closed under multiplication. So here we have a set of elements. Each element is a 2 by 2 matrix and is closed under multiplication. Is there an identity? Well, if you take I to be the matrix M0, so that means you have a 0 in the upper right-hand corner. This is an identity under this under matrix multiplication. So this is the multiplicative identity in H. And matrix multiplication is associative. At some point, I'll write out the proof of this. It's just a little calculation. But for any matrices, take 2 by 2 matrices, for example, the matrix multiplication is associative. And if this is the identity, what is the inverse? What is M sub A minus 1? What is the inverse of this matrix? I claim it's the matrix 1 minus A 0, 1, because M sub A minus 1, well, actually, so this is M sub minus A. The matrix M sub minus A is a minus A there. And, well, if I take M sub A times M sub minus A, this is the multiplication rule. MA, MB is MA plus B. So MA, M minus A is MA minus A, which is M0, which is the identity. So the inverse of M sub A is M sub minus A. So in this group, every matrix has an inverse in the group. So this set of matrices is a group. It's a multiplicative group. And I claim that the group of integers under addition is isomorphic to this group. This is the symbol for isomorphism. So in order to prove this claim, I have to construct the actual function. So we define a function f from the integers to this set A by f of the integer A is the matrix M sub A. So the number A gets mapped to the matrix M sub A, which is 1A, 0, 1. And F is 1 to 1 and on to. So I must prove that for all integers A and B, f of A, so f of A is something over an H, f of B is something over an H, and I can multiply those two matrices. That's the same thing as f of A plus B, which is the binary operation in Z. And the proof of this is right away, is immediate, because this is true because f of A, f of B, that's the matrix MA times the matrix MB, which we saw was the matrix A plus B, is f of A plus B. So this very simple function is a 1-to-1 and on-to function from Z to this matrix group H, and it has the right multiplicative and additive property. So the integers under addition is a group that's isomorphic to this set of matrices under multiplication. So even though the elements of the groups look very different and the operations are very different, we do have isomorphic groups. So this is a nice example.
Hello.
Mm-hmm.
Yeah, a couple more questions. So, in terms of this isomorphism, isn't the same thing can be achieved by comparing cardinality, or is this more useful when you have countably infinite sets or infinite sets?
So if two groups are isomorphic, they have the same number of elements, the same cardinality. But there are many different groups that have the same cardinality, but are not isomorphic. So let me give a simple example. So suppose I let G be the group of congruence classes mod 4. So this consists of 4 congruence classes. And just for simplicity, I will write A bar to mean the congruence class A plus 4Z. So we have 0, 1, 2, 3. So this is a group with 4 elements. The cardinality of a group, so the order of a group G is the number of elements in G, which we write as G with absolute value signs around it. So for this group, the cardinality is 4. And addition is just addition of congruence classes. Now there's another group which has a name, I'll call it V. It's called the Klein 4 group. Klein was a German mathematician, and in German, 4, it means 4. So that's where the V comes from. So this has 4 elements. I'll write them as E, A, B, and C. And the addition rule is, well, I'll write down the addition table. E, A, B, C, E, A, B, C. So E is the identity under addition. So this is E. And anything you add to itself gives the identity. And A plus B is C, A plus C is B, B plus A is C, B plus C is A, C plus A is B, C plus B is A. It turns out with this addition, or this binary operation, it doesn't really matter whether you write it as addition or multiplication. Maybe I'll write it as multiplication. So this is a group. This has 4 elements and this has 4 elements. But these groups are not isomorphic. They have the same number of elements. There are lots of one-to-one and onto maps between them. But maybe this is a homework problem, so I don't want to do it, but it's something to think about for a while. These
Actually,
groups
Professor,
are not isomorphic to each other.
It is actually problem number 4 in homework, except for the fact that the problem is incomplete. There is no question added. There's just description of this Klein group and the binary 2-digit 2-bit addition or something.
Oh, okay. Thank you. That's just, yeah. So I had corrected that, but that's not what I will change that and upload it to the website as soon as we finish today.
No problem. So in order to clarify my question, I think I kind of got the answer, but I just want to make sure that it's the right answer. So 2 groups can have the same cardinality, and you can have a one-to-one, or basically one-to-one and on-to function from one to the other. But in order to be isomorphic, they also have to sort of perform the function also has to basically have additional properties where x1 plus x2 or x1 times f of x1 plus x2 be equal to f of x1 plus f of x2 in both of them. So basically y1 plus y2 has to be y3 if x1 plus x2 is x3, in the original function.
Well, so one way of understanding isomorphism is if you take a group, write
Mhm.
down its multiplication table.
Mhm.
Just change the names of all the letters. So you don't change the multiplication table, you've just like renamed every variable.
Right.
So that's essentially the same group, it's just that you've renamed the elements. So
Right.
that's exactly what isomorphism means. Two groups are isomorphic means if you were to write down the multiplication tables for them, there'd be a way to change the names of the elements in one without changing the multiplication table, and you end up with the same multiplication table. That is.
Okay, so it's more restrictive than just having a one-to-one and on-to function.
Oh, infinitely more restrictive. You can have millions of different groups of the same cardinality that are not isomorphic.
Understood.
May you show the page before this again?
Sure. Anything else? Questions about anything?
I just have a question really quickly. If when you multiply the two matrices,
Yes.
the MA and the M sub B, why isn't it AB when you multiply it? Why is it A plus B when you multiply it?
So the rule for matrix multiplication comes from how you multiply a row and a column. So if you had a row, let's say they're just two elements. This is, let's say, R, S, T, U. The way you multiply the row into the column, you get the number RT plus SU. And matrix multiplication comes from multiplying rows into columns. So in the matrix MA, this is 1A01, and this is 1B01. So when you want to get the number that ends up over here, you're taking the second row and multiplying it into the second column.
Okay.
You get 1 times B plus A times 1, which is A plus B.
Yep, got it. Perfect. Thank you.
Sure. Anything else? If not, I'll be back at 4 o'clock today.
Thank you.
And as soon as I get done, I will clean up that problem 4 in section 1 and repost it on Blackboard. Okay, bye everybody.